All right, good morning, everyone. I'm Mikhail from Igalia, and today I'm going to talk about a RISE project that just finished in September that had the goal to improve performance of the code generated by LLVM for RISC-V. And since the submission of this talk, I'm happy to share that we no longer have just a 15% improvement in performance. Now we have a 16% improvement in performance. Yay! Yeah, it's a small but still measurable improvement since we submitted the talk, so that was nice. Okay, so as I said, this was a RISE project. It ran for about 10 months. And we had a target board, which is Banana Pi BPI F3 with a space meter 60, which has a in-order RISC-V processor. It supports the RVA22 profile and RVV 1.0. And the goal was to try to close the gap between LLVM and GCC. And the results is that in some benchmarks, we have individual contributions that increase the performance of the code generated by LLVM by up to 16%. So prior to this work, there was a clear gap between LLVM and GCC. That was the motivation for this project. But during the project, we noticed there's no single solution, especially on LLVM, which has a lot of activity day to day. We see a lot of regressions, improvements, and we have many contributions, but we're going to focus on three main contributions. Scheduling model for the X60, some improvements of vectorization across calls, and IPRA support for RISC-V. And the contributions, we're going to start with the major contributions first, which was the scheduling model for the X60. So basically, scheduling, instruction scheduling translates to performance. If we have wrong latencies or resources, the compiler will make some poor choices. And I'm going to show an example here very quickly. So on the left is before the scheduling model. We have a load that loads from memory to FT0. And then right after, we have an add that uses FT0. And because the load takes a few cycles, the processor just stalls. This is an in-order processor, so it just stalls. And then after that, we have a multiplication that doesn't use either FT0 or FT1. So what the compiler can do is reorder that. So we have the load, and then now we can issue the multiplication. Once the multiplication is done, we issue the add, and now the cycles that it took to load to FT0 was hidden by the multiplication. So we just execute it. So we save we save the stall there. And how do we get the numbers, right? So how did we collect the latencies? We had to write a micro benchmark tool to collect them all. That's for latencies. For throughput, most of the instructions, throughput data was already available from Camel CDR. We just had to implement a few. But this, as you can imagine, is a massive piece of work. Because even though RISC-V is RISC, we have more than 9,000 instructions. Not exactly instructions, but the RVV, since we have different combination of elmos and element width, we have to take them all into account. So I have this massive spreadsheet with the latest of all these instructions that, once collected, needs to be added to LLVM. So this was a massive piece of work during the project. And what about the results? So we are using SPEC, and we had, this is RVA22, no vector extensions, and we see that there's up to 16.8% improvements, no regressions at all. If we take the geomean of this, we get almost 5% improvement in execution time. And now these are the results of RVA22 plus the vector extensions. We get up 16% again, but the geomean is slightly lower, which is 3%. But still, we get improvements on both non-vector scalar code and vectorized one. This, actually, that was a very surprising result once we had the scheduling done, which was that once it was, we finished the scheduling, it almost removed the difference between scalar and vectorized code. There's a single benchmark where vectorized code is faster using on SPEC, which is X264R. And our hypothesis is this happens because this is an in-order processor. We assume that if we are dealing with out-of-order processor, the vectorization will be much faster. But for our cases, it's just a single benchmark that is faster. Okay, so improvement to vectorization across calls. That was, when we were analyzing the code, we saw there were benchmarks that were faster when compiling with just scalar compared to vectors. And the analysis showed that it was just spilling. We were spilling vector registers, and this was causing the regression. And this was happening particularly around function call boundaries. I'm going to show an example. This is from NAB-R, and we have a function with 4 blocks, and on the left you have the, oh, sorry, on the right you have the graph of it. So what happens here is we have a load from P, then we have a second load from P, a conditional jump, and then we go to either foo, which has a function call, or bar, which also has a function call, and then on the last block we do a store followed by a second store. And because these regions are continuous, we can vectorize them. But the problem was the SLP vectorizer was like aggressively looking at the blocks, just the blocks where the load and stores were happening, and checking if they were profitable without checking anything in between. And it would just ignore the 2 blocks that had the function calls. So what happened was those 2 blocks were not taken into account when calculating if vectorizer code was profitable. So that's a nice story for this, because we sent a patch to fix the issue, and we had amazing results. We had almost 10% improvements on app, but there was a drawback. We increased the compilation of up to 7%, and that would happen just to see, but there were other slowdowns in SPEC. And then after we submitted the patch, Alexei Batev, which is the SLP vectorizer code owner, proposed a refined solution, which I'm going to show the results in a bit. It's even better than those numbers that I show, and doesn't regress the compilation time. I think this is just to show the importance of the community. Even though we did the investigation, the end result is that we have a better LLVM today. And these are the results. So NAB with Alexei's patch up to almost 12% improvement execution time. And this is just for vectors. So remember, the vector code was lower because it was spilling vector code. And what happens now is that we no longer, when we enable vectorization, we no longer vectorize those calls. We just use the scalar because it's faster. If we take the geomean, it's almost 1% improvement on execution time. And the last contribution was IPRA support for RISC-V. So the goal here was to try to save cycles of spilling registers. Basically, the LLVM would take a conservative approach when writing prologues and epilogues, and it might be spilling registers that don't need to. So again, an example here. So we have a function foo, and we have 2 registers. Let's assume those are not live in the function, so S0 and S1. What IPRA does is just remove those spills. There's no save or restore there because they are not needed. So yeah, IPRA it causes a shorter prologue and upload. It reduces register pressure. I'm going to show the results. They're small, but we can consistently measure them. Unfortunately, now we cannot enable IPRA by default because there's a bug open for a few cases where the compiler just crashes, but it doesn't affect SPEC, which are our benchmarks. So this is RVA 22, no vector extension. We got up to 3% improvement when IPRA is enabled. We get a 0.5% geomean. And this is RVA 22 with vector extensions, and we get a 0.39% improvements. Again, these small improvements, but they are consistent. And were the biggest contributions. As I said, the scheduling was the most important one. Would provide the largest wins. Vectorization IPRA is smaller, but they're consistent. Almost all the contributions were already upstream. We still have 5 PRs under review, and I'm going to apologize to the reviewers because I'm going to nag you here in person to review my PRs, please. They're sitting there. I'm going to chase you here at the conference to get some reviews. Yeah, so what we learned, having a schedule model is critical for performance. LLVM was just specifies the code if we don't have it. We should likely at some point try to have a default scheduler for RISC-V. Some other targets do. ARC64 has one based in a board. And who knows, maybe we can use the X60 given the numbers we got. Another conclusion is that not all the contributions have immediate impact on benchmarks. At the start of the project, I spent a long time just writing the right cost for individual instructions, but it wasn't until I get the whole scheduling model done I saw the results. And vectorization is hard, and we have to be very careful when we are tuning for vectors to avoid regressions. And the question is, did we close the gap between LLVM and GCC? So I'm going to show you here a comparison of the SPEC compiled with the LLVM and GCC. And I just wanted to, out of the gate, say it's not an apple-to-apple comparison. Both compilers, or both extensions were, for both compilers, the extensions used were the same. But as far as I know, when I was doing the test, GCC doesn't have any X60 specific scheduling latencies, what LLVM does. But we still think it's useful to see how LLVM caught up with GCC. So this is SPEC RVA22 with no vectors enabled. We see that we can be up to 27% faster, but we can also be almost 27% slower. So I think we are almost there with in GCC. There's still X264. We still have to look why we are being so slow on scalar code. And for vector, we have a similar case, but just the percentage is smaller. We can be up to 8% faster, but we can also be 9% slower. Yeah, that's it for my talk. I just want to thank RISC for sponsoring this project, my friends at Igalia for the discussions and feedback, and the LLVM community for reviewing the patches. And before I finish, I just wanted to share what else we are doing at Igalia related to RISC-V. So we had a talk this year on the Euro LLVM by Luke related to data flow analysis. And on the RISC-V summit in Europe, we had another talk by Luke and Alex about vector code generation. And now we provide at Igalia also a nightly test build for RISC-V on the X60. So we have for both GCC and Clang, LLVM Clang. And you can see we check, you can see the results daily of the top of 3 in both repositories. And that's it. Thank you.
Thank you for that 16%. But I was in the compilers like in 80s, and the first example you shown, this is in my opinion like how come the compiler can do that scheduling it was showing like on the left, right? It was before the instruction was obviously incorrectly scheduled, so you fix the bug in my opinion, and maybe many others as well. I mean, they look to me like very immature compiler before you've done what you've done. I'm not a compiler expert, but some of these things like could you show the first?
Yeah. Like, yeah, no, I understand, but it is just an example that this sometimes happens. This is a very simple example. I don't expect LLVM to do that, yeah. But this is just an example of what might happen. I move here.
Yeah, like that instruction ordering, right?
Yeah.
The one is simply you are just will never be better. That's my opinion.
Yeah, it's a very simple example, right. Just to so you can understand
just a note.
What's going on.
I wasn't aware there's such a big difference between compilers exists. Thank you.
All right.
I know this may sound like a bit of a noobish question because obviously I'm not as well versed in compilers as many of the veterans here, but I'll just take a shot at it anyways. You said this was done with the SpaceMint X60, and that provided some performance benefits with instruction rescheduling.
Yeah.
But with the up-and-coming release of the SpaceMint X100 and X200, do you expect any differences in how compiler optimization will happen, and if so, what can we expect?
So it's very hard to answer because, as far as I know, the X100 and 200 they are out of order processors. So I just don't know if this will impact them or not. Yeah, I think we're gonna have to get some data on that first.
So you're probably gonna have to do a bit more research on that.
Yeah.
Okay, that makes sense. All right. Thank you.
Great talks, and
Thanks.
sorry, I have to review those 5 patches.
Thank you.
Yeah, so I'm curious about the gap between GCC and LLVM. You mentioned, because I remember GCC, it only uses SLP. It doesn't have loop vectorizer. It tries to vectorize the loop with a special version of SLP. Do you have any insight on that? Like, there's 2 completely different styles of vectorization, because LLVM does have dedicated, V-plane or something. Do you think that will be a factor, and any comments on the differences?
Very hard to say. I'm not working on that anymore. Luke is working on that. So Luke, my colleague from Igalia, I think he's the best person to answer that. But yeah.
Thank you.
Yeah.
What GCC version were you using there?
Oh yeah, I forgot
Because
to
the
mention
GCC
that.
version at
It's
GCC
15
14 and before,
Sorry, it's
auto vectorization is not good.
Yeah, it's 15.1 is the one on the latest Ubuntu LTS, I think. Yeah, I just say 15 here, down there, but I think it's 15.1. It's not the latest and unstable one. The latest unstable one, you can see the results at the cpath igalia.com. Yep.
Hi, great talk. I'm not a compiler guy, but I didn't see any mention of out-of-order cores comparison. This was
Yeah, we didn't. We only use that board to compare our results, both GCC and LLVM. Out of order, it's another completely different world. We didn't want to compare with that.
okay.
Yep.
Thank you.
All right. Thank you very much.